Okay, so as I told you, post-sector graph comparison, there are many comparison. One important comparison is by me, and it tells that you take two graphs, okay, and let's suppose that post-sector. Adjacent is post-sector, we are discussing. So let's say G and H are two graphs, and they are given as post-sector. Okay, then we can get some examples like a smaller number of vertices. So now you have to look at, suppose that there exists a vertex B in your G and another vertex B yes in your H. So if you delete E from G and B yes from H, they are also posting. Okay, so you started with two graphs, they are post-factor. Now we got two vertices in both, and after deleting, they are also becoming post-factor. Then what you will do, you choose any other graph. Okay, gamma is any graph, you can choose. Okay, and what you will do, you take gamma and fix a vertex in gamma, that may be you. Then you make a coalescence at C with the vertex B, and at your C, the other graph is H. There you will make the coalescence at B, okay, of gamma, and you make two other graphs. Okay, so what I'm saying is, I know that G is a graph and H is a graph. Here I know that there is one vertex that exists, so that G minus P my concept is graph, and here there exists one vertex media, so that I can take this graph, and I'm given with G and H both are calculated, and these two vertices are in such a way that if I delete them, okay, then this graph and this graph both are post-factor. Okay, In that case, I can choose any other graph, gamma, and I'll fix a vertex. So this is, let's say, gamma. Here I'm fixing a vertex say 2. Here I'll do the constants, then so I'll just start testing at that vertex. So here I'll put gamma. I'll put okay. And in the key vertex of gamma, we are here attach. Sorry, U vertex. So U will become radius. Okay. So now these two graphs also will become cosine. Okay. So the third graph, you can choose any graph. So we started with two co-spectral graphs, and then somehow we have to have two vertices in those graphs. So the deletion also makes co-spectral. Okay. Then we can attach any other graph, and we can obtain co-spectral pairs. I will give one example. Okay. Otherwise, you cannot have. So here is one example. So I am taking G, same as H. Okay. And G is this tree. H is also, I take the same. Okay. So G is same as H, so they are co-spectral. G and H are co-spectral. So the same graph is thing. Okay. Now look at the vertex V I have to there. And V yes. Okay. If I delete V from the graph, what I will get? I get a path of product V this side, and another this side is a path for each vertex. Okay. So how many vertices are there? 6 vertices. 7 vertices in the second point. So one will be P will be deleted. So you will get a path of order 3 as a component, and another is a path of order 6 is taken and one again with one pendant desire. So 7 vertices that graph. That's the known as Z7. That's graph. So if I delete G, what you are getting? Same you are getting. So they are also co-spectral. Okay, so in when you are thinking G, you take V. When you are thinking V as H, you take radius. Okay. But after deletion of P and radius, both the graphs are same graph. Okay, so they are also co-spectral. Right? So then if I apply with the operation, I can take any other graph. I'm choosing let's say P. Okay, gamma I chooses P. Right? So from P3, I am choosing the vertex US, that is V2 vertex. Okay, and I'll make the operation. Just I'll attach. So P3 you take, and the V2 vertex you are attaching at V. Okay, in both the cases. Now the graphs are defined graph type. You can looking at the graph, you can say that they are not reciprocal, but they are co-spectral. I took PNG, but you can take any other graph and you may arrange graphs or trees. So there will be first of so many co-spectral here. Right? So this is one way to construct co-spectral pairs. So as I told, there are several construction methods to construct co-spectral pairs. So that we prove this theorem that with respect to the adjacent symmetries, almost all traits are not determined by space. That means there are co-spectral pairs. Okay, but then also there are in fact many graphs which are determined by the space within space. Okay. there is another method also that's known as Gaussian matrix switching. So there you can take the matrix and do the switching. And this method works for adjacency, Laplacian, and also for like Seidel matrix, which are obtained from adjacency matrix, Laplacian matrix, and all ones. Okay. So here I'll tell you about how to apply the method for adjacency matrix, but the same can be applied also for Laplacian. Okay. So the rule is saying, or the construction is in this way. First you have to choose a matrix n. That's a 0, 1, okay. And it can be a rectangular matrix, so size is like B cross C, you can choose. But you are putting zeros and ones, but in such a way that every column you should have either zeros, ones, or B number of ones, or B by 2 number of ones. So that way you will construct a matrix. Okay, that's the matrix you are constructing, that is B cross C. Means the size is B cross C. Okay, and once you have that matrix, then you take another matrix which is a symmetric matrix and B cross B. Okay, that's a 0, 1 symmetric one. So that can be taken here as symmetry of some graph, or you can form. So you will take a matrix B. Okay, that's a symmetric matrix. But the condition is it should have constant row and column count. And then you choose C as any matrix, which is a symmetric matrix of size C square. C cross. Okay. Now you form the matrix M, that is the bigger matrix, where you are putting B first row and N transpose S. Okay. Now observe that N is a matrix which is with 0, 1 and 3, then somehow we have chosen the columns in such a way that like either you have all zeros in the columns or all ones in the column or half of your ones are there. Okay. So now from N you can have another matrix N dash, where if some column is containing B by 2 number of ones, you just change with B by 2 number of zeros in those places, and other places where there is 0, you have to change to 1. Okay, that's the switching you did. Where there were 0, you have to look at the columns where half of the entries were 1 and half were 0. Okay, now you are changing and getting another matrix that is N dash. Okay, so then using N dash I can make another matrix similar way. So there B and C are fixed. Only in place of N I put N dash. Okay, then both the matrices will be similar matrices, so they have the same idea. So you can make C can be chosen any matrix, but if I choose B as 0, 1 matrix, symmetric matrix, and C also 0, 1 matrix, symmetric matrix, then the way we are taking N, this will correspond to some graph, right? Adjacency matrix of some graph. And the other matrix also will correspond to some graph, but the edges we have changed. We have taken the edges where they were. We have just changed them, right? Half of the entries in those columns, we have made 0 as 1, 1 as 0. So edges are changing. So that means change the graph. Okay, so if both the matrices means they correspond to different graphs, if they are not isomorphic, then we can get co-spectral pairs. Okay, but it may happen that there will be isomorphic. But if not, then the way we have constructed, they are similar matrices, then we can prove it. So they will be having some spectrum. Yeah, so this is another way of constructing. But this is one type of switching. There can be other switching also. You can also define like in the matrix. Okay. I have not checked, but you can check. So here both the matrices are similar that you can observe because they will, because if you take Q, Q is the matrix defined in this way I have written. So you can show easily that M dash is nothing but Q and Q equal. Can you do this one? So the multiplied block ways is matrices are blocked. There is the odd ones matrix. What is the inverse? So the one that if you are done, so you can discuss the class if somebody is not on. You just have to go ahead. So as I told you, can apply this technique to the question also. And while applying your the m is minus l, okay, because there is a question of diagonal entries and everything. So taking this, if you apply, can be done. So I'll just give you one example that how it's happening. Okay. So I took these two graphs and their matrices are showing here just how it's happening. So these are the two graphs. The corresponding Laplacian matrices I just put negative sign. So you can observe that the switching has been done similar way. So what should be your first matrix be? P is 4 cross 4, right? P should be the matrix, symmetric matrix with rows and columns are constant. Okay, and here M is the matrix which is in the right, like 4 cross 4 block. Okay. And in the other matrix, you can see that where I had ones, I put zeros, and where I had zeros, I put one. The N and N, yes, you can observe. So this was your N matrix. And there you can see the ones and zeros are interesting. Okay, so from this matrix, the other matrix has been obtained by doing the method, whatever switching method. And the corresponding graphs, like for the corresponding Laplacian matrix, I have drawn the graphs. Okay, so as per the method, both are same spectrum, but you can see the graphs. Are they isomorphic? Why they are not isomorphic? For cycles, not messy. The first graph has a 4 cycle, And in the second graph, there is no person. Okay. So this way can be constructed, but I just told this is one way of like change has been done in certain part of the block, and this way this is one way. But you can think of another switching also. Okay, that is one way approach, like one way that is. But there are other also changes we can make in the matrices, and we can form both because. Now, you what you were asking about integral eigenvalue graphs. Okay, graphs with integer eigenvalues. So, graphs with integer eigenvalues are known as integral graph. Adjacency eigenvalues are all integers. And we also observed that those graphs are not coming frequently if we are considering adjacency spectrum. Okay, so you know the complete graph is with integer eigenvalue. Stars are integer eigenvalues. Only if your eigenvalues are root n minus 1, 0, 0, and minus root n minus 1. So it will depend on n, and then you may get integral graph. But in Laplacian case, graphs come frequently which are integral graphs. Okay. But these operation also you know union operation. So if I take union of two graphs, you can express the spectrum in terms of the original pictograph. Okay. So what it will be? Eigenvalues will just be union. Because the matrix, whether you are considering adjacency or Laplacian, the matrix can be written as a block matrix. Okay. So here I am considering Laplacian. So for the Laplacian, eigenvalues are just union of eigenvalues. Okay. So then the two zeros will come because the graph is disconnected. Now the join operation you already know. So the eigenvalues I am saying that they will be this. If the eigenvalues for G are 0, lambda 2 to lambda, and the eigenvalues for H are 0, mu 2 to mu m, then the eigenvalues of G join is they will be lambda 2 plus n, lambda 3 plus n, those will be n minus 1 eigenvalues. And then I have mu 2 plus n, so mu n plus n, those are n minus 1 eigenvalues. 1 0 will come and then n plus m. So you know how these are coming. You can compute. So join the join operation you know, right? So what is join operation? You have to take the union of G and H. So you are putting one copy of G and another copy of H. Now from every vertex of G, you will put H to every vertex of H. Okay. So from here, you will put like every one H. Okay. If I take like this one as one hash graph, that is P2. And let's say the field graph I'm taking K1. My joining is to double. That will give me a complication order. So this is the join operation. Okay. If I do the join, then what will be the adjacency matrix of the join? So here I'm not making any change, right? All the addresses are there. Here also all the addresses. Only new addresses are. So adjacency of join and taken H. So you will keep your adjacency matrix of G if I am taking these matrices first. So the vertices of G and then vertices of H and so here the adjacency between the vertices of H are there. So I'll put here. Okay. Now here some entries will come which are between the vertices of G to H. And those we have to make all it. So this will be okay. So this is the adjacency matrix. And then what will be the lambda cell? So can I express the Laplacian matrix in terms of Laplacian matrix? So here L of G will put and degrees will increase because this is just so how much I should add? N will right? So N times and this will be minus. And similarly we will happen here. Okay. So now if I know the eigenvalues of G and H, the Laplacian eigenvalues, can I obtain the eigenvalues for joy? So how to do it? So let us take all the eigenvalues and eigenvectors because in last class I told you was using eigenvectors. So I have taken care eigenvalues lambda 1 is 0 and then lambda 2 to lambda n. Let us take the vectors also. So here you have all one vector that corresponds to 0 eigenvalue and its size is and then here you will have one eigenvector. We also observe that if I choose any other eigenvector within the all one vector, they are orthogonal to all one vector. That also we have discussed. So in this like for these vectors, I know that the sum of all entries is it. Okay, they are orthogonal to all one vector. Similarly, I'll take the other one. And let's the vectors first. Now, can we use these vectors and their eigenvectors for the job? Can do. So what should be? Okay. So I is saying that I'll take this vector xr or you can first think of which one. Whatever. So any xr I is 220. And this is my first block and then the other part I am if this will give let's say we're starting with this matrix into this vector, what do you get? Or this is H or this should be multiplied. So you can compute and then fill in the last one. So this is LG XR. LG XR is mu XR. The mu Y XR. Sorry. And then M XR. Okay. And this part will be multiplied with J. This part will be multiplied with x star. And this is all ones vectors are there and row and column. So if I multiply with this, I get 0. So what I get then? E1 plus 5 plus NB. Right? And then okay. Then I can, because below part is 0, I can make that constant. So this will be I should take a lambda. Okay. So this is true for any I equal to 2. So this way you'll get your lambda I plus n as eigenvector. Okay. The same thing I can do for yi's. I can construct the vectors between here 0 and here y or y's. Okay. So that will be the order eigenvalues vector of the form mu plus n. And 0 is one eigenvalue that will correspond to all ones with. So that is. Then the last one is m plus n rating, then how it will come. If you want to look for eigenvectors, you have to choose one eigenvector which is orthogonal to all the eigenvectors we have taken. So that way we can. If I don't want to calculate the eigenvectors, can I say from the trace sequence? So what is the trace of the vector? One eigenvalue is left here. So I can get it from the trace, right? And what is the trace? This is your matrix. So what is the trace of the matrix? So here sum of the degrees, and then this will be n times m. So you can write down. And sum of the degrees is what? They want to write it anyway, right? And then we plus mn, right? And then this part, similarly. Okay. Now you have already those eigenvalues. And those eigenvalues are covering lambda 2 to lambda n. Okay. That will give you this lambda 2 to lambda n, this will come. Okay. This is what? Sum of all eigenvalues. This is sum of all eigenvalues of your hash graph. And that is what? Lambda 2 to lambda n. This quantity is MS summation of lambda n. This quantity is MS summation of lambda n. Oh, we want. Okay. And how many m's are there? Already stated. M into n minus 2. And there are how many there? N into n minus 2. Okay. So those are already taken. So what's remaining from the total structure? M plus n, right? So m plus n is one item. But you can keep based on what is the eigenvalue. And for the complement, the eigenvalues will be 0 and n minus lambda I. Can you prove this? For the complement. If I know the eigenvalues of G and those are 0, lambda, 2 lambda, then I can say the eigenvalues for the complement of. So complement means that is another graph, right? G and G complement, and in the complement which addresses are there, those are not there, and vice versa. Can you prove the third part? So if I take LG and LG complement, okay, both if I add, I take all the edges of G and all the edges of G complement and form the graph, what it will be? Complete graph. Okay. So if I relate LG and LG complement, I add them, what it will give you? Representatives of the complete graph. So from there you can, you know. For the complete graph, whatever you need, that you know. And you will send method. Okay, so it is obtained. And these three things will be used frequently. So that I get it. Now, as I told, I'll discuss about Laplacian integral graph. So the first example is a complete graph that already you know. Okay, that has the eigenvalue 0 and if I take a star, there is also with the spectrum all integrals, right? And we have also discussed like this is the only tree which is with all eigenvalues in it. So this is characterized. So in case of trees, all the integral trees they are characterized. They are only stars. Okay, because what we observed, like if I take any other tree, then the algebraic connectivity that will be less than 1. So there the integral. But one can obviously look for like trees with how many ones you want there. Like trees with like 3 ones or k number of ones. Okay, that kind of problem also one. But one nice thing is this is like complete characterization of trees with integer eigenvalues is done in Laplacian case, whereas in adjacency case we have no such information. Okay, the complete characterization. So Laplacian integral graphs, like as I told, studying those is more interesting than adjacency. So these two graphs also determined by the spectrum that we studied earlier. So they are determined by the Laplacian spectrum. Now there is another class that is denominated co-graph class. If some of you heard about threshold graphs. Threshold graphs are also co-graphs. Okay. So here the construction is in this way. You can think of like K1 is a co-graph that is static, and then complement of the co-graph is also co-graph. Okay, and union of two co-graphs is also a co-graph. If you want to avoid complement, you can put a join also. Because join is join of two graphs can be taken as take the union and the complement. That will be join. Okay. So in some book you can say that join and union are co-graph. So how you construct, basically you start with the singleton vertex, you can take another singleton vertex and join them or take the union. That is a co-graph. Okay. I can take another vertex, I can join or make the union, that is a co-graph. Now if I have co-graphs, I can take two co-graphs and then join them or take the union, that will be a co. So when you are making the co-graphs, so if last step is complement or join, then you are getting a connected graph. Last step is union, then you are getting a disconnected. Okay. So here threshold graphs can be obtained where like when you are doing the join or union, you don't have to take two co-graphs. You have to take a co-graph and this new one you will add that it must be K1 in single vertex. So if that restriction you will keep, then it's threshold. The co-graphs have any union or join you can take. Before. And co-graphs, the way we constructed, we started with single vertices. And then the operation we are using either complement union or join union, right? So the eigenvalues, if I'm starting with K1, I know that that is an integral graph. And when I do join with another K1, that will be P2 and that's integral, right? Each step I'm doing union or join. So my integrality will be there. So each time I'm getting an integral. Okay. So the way they have been constructed, you will get Laplacian integral equation. So here you can see example. So I have taken like K1 union K1. So that's co-graph, right? And it's Laplacian integral. The eigenvalue is 0 and 2. Now I'll take another vertex. Now I'll just join. Okay, so I got P. Okay, what are the eigenvalues? 0 and 2. This is complete terms. You can think in P for K. Okay, so 0 and 2. So these are integer eigenvalues, right? And next I am taking another vertex and making union. This is also co-graph. This is a disconnected one. Okay, what are the eigenvalues? 0, 0, 2. Now I can join. Okay, this is another co-graph. What are the eigenvalues? Okay. Now if I take another two vertices. Okay. Another two vertices I'm thinking as one co-graph. Okay. And then I'll join with this. That's another co-graph. Okay. Your first graph was K3, that was with the laser spectrum. And then you took two vertices only, those are 0, 0 spectrum. That is 0, 0. Now you made the join. So you can calculate the eigenvalue the way we have done. Okay. For the join, I told you what will be the eigenvalue. So they will increase by m and then and 1 is m plus n. Right? So all will be increasing. So for this graph also all eigenvalues are good. This is another code. Okay. Similarly, we can proceed with another code. So these are all co-graphs. Like Richmond co-graphs are getting constructed. So they are with Laplace and eigenvalues as integer. Okay. So this is one nice class. But there are other classes also constructed. So one operation that they use to construct the Laplacian integral graph is by adding one edge. Okay, that's the most fundamental operation. Adding a new vertex or adding one edge which is not present. So you can get another graph, right? So this edge addition has been used to construct the Laplacian integral. Okay, and it's how it's done. So there is the. So it was method was proposed by Iwsmga, and then he first thought about doing in this way, constructing Laplacian integral graphs from the known ones by adding one edge. Okay, so what happens if we add one edge of the matrix function? I'm defining this vector, this and this defining so that we can write it nicely. So here is a denoting as a vector which is with I component 1 and j component -1. Okay, that means I can write ei minus ez. EI is the standard unit. Okay. So this way if I define the vector. So if I am taking one graph, let's say G is one graph. And I know that these are two matrices I and Z, and they are not adjacent. If I adjacent, I will add when we create a polygraph, right? So we are like doing simple graph. So let's say I are not adjacent. Okay. And I want to add one edge. So that is my new graph. So this edge may be, let's say, D, or you can think I did. So you have another graph that you can see plus I. This edge you add. Okay. So what will be the change in the matrix? So you'll apply some matrix here, here. And I look at the only change I'm doing here only I change. Okay. So I look at the I flow, J flow, I follow, J follow. They are the change here. Okay. So they were not adjacent. I J were not adjacent. Okay. So the degree was coming from other vertices. So here some degree was there here. Here some degree is. This degree was 0 because they were not adjacent. Okay. And other things will remain the same for the new graph. Okay, now we are adding the edge. What will we have? So here we will add the one degree, right? So this is 1 and this is -1. So this change will happen. So if I write as like matrix form, I write this as this. Because some matrix are fine. Okay, what is the matrix? So everywhere 0 and 1 -1 -1 1. And if I am taking E, Ij is the vector, then you write in terms of Eij. Eij is the vector with I think you want Eij into Eij transpose. Eij transpose into Eij will give the next one. So 1 plus 1 and 2 plus 2. But the other way. Okay. So Eij transpose. We're not able to figure it, let me keep like this. I wrote in that way because you already read the positives and negatives. So if this is the transpose, so this is a EI J EI is a transpose. So this is a positive and matrix, right? This also we discussed. If some matrix can be written as P into B transpose, then the matrix will be positive and so you are adding a positive and matrix to LG to get LG plus. So how the eigenvalue will all the eigenvalues they may increase and they will increase. That's what position. Okay. So how can I write the eigenvalues? So let's say lambda G I'm using for eigenvalues of G and lambda G plus used for eigenvalues of G plus. So what I can say is all the eigenvalues are getting and they will increase. So lambda 1 G that is 0. That will be less than equal to lambda 1 G plus. Okay. And that will be less than equal to lambda 2. Number of eigenvalues 7 because we are going to increase by this. Okay, so all the eigenvalues they are increasing or remaining 7. Okay, but total increment number is sharing that. You have just added one edge. Sum of the eigenvalues is sum of the degrees, right? So degree has been increased by 2. The total increment is 2. So if I look at the sum of all eigenvalues, lambda and g plus c minus the sum of eigenvalues of g, the total increment is 2. This is sum of degrees, right? Okay, so eigenvalues are increasing, but total increment. Now our thing was with integral graph, and can we use this constant integral graph? So if I start with the integral graph, let's say, and by putting on S, I want to construct another integral graph. So what I should look at? I should look at my increment should be in integer, right? And total increment is 2. So what are the options? That how the change should occur? 2 eigenvalues can increase by 1 and 1 each, right? Or 1 eigenvalue can increase by 2. In that case, the integral relation will happen. Okay, that's known as the integral relation. So either 1 eigenvalue will increase by 2, other eigenvalues will remain same. Okay, or 2 eigenvalues will increase by 1 each, and others will remain same. So we say that the integral relation occurs at one place if 1 eigenvalue is increased by 2, and it occurs at 2 places if 2 eigenvalues are increasing by 1 each. Okay, and this is known as integral relation. These two things can occur if we are looking for variation by integrals. And if G is Laplacian integral, so if this will happen, this type of variation happen, then we can get another integral by adding this. Okay. So when the first case will occur and when the second case will occur, both are characteristic. Okay. So for which what should be a condition in a graph, or where you are putting this S, like this I and Z. Okay, what should I put the condition on these two vertices? So that when I add integral variation will occur. Okay, that has been done. So you can go to the paper by watching so or Han, and then you can get where the variation is occurring at one place. So for which graph the variation will occur at one place. You can observe there the eigenvalue that will increase. Okay. So the spectral variation will occur at one place when these two degrees are same and their neighborhood set is same. Okay, so these two vertices will be adjacent to some vertices which are common to both. Okay, so their neighborhood sets are same. So degree will remain same. In that case, this degree will be one eigenvalue for the graph. Okay, and that will change by 2 when you will add that. So that is the spectral integration will occur at one place. Okay, spectral integration occurs at 2 places. That has been also described, but not in that way structurally, but for the matrix, so that Dr. Jansen has described in his paper. So its complete calibration is that when the spectral integration will occur at one place, when 2 places. Okay. So then the operation, this operation can be used continuously, and you can go to construct Laplacian integral graph. Okay, and the construction also like repeated application and how it can be done fully. That problem also completely done. So You can see papers by Kaushal. 2 papers are there for construction. Laplace and real graphs using AZ. Okay. Now, one can also think like what we discussed. Looking at this, one can ask the question like if we can ask question. When a graph has one eigenvalue as n will be the largest number we can think of. Okay, which can be eigenvalue. So when a graph has n as one eigenvalue, so that is one question one can think. And it can think of when a graph has one as one eigenvalue. What do you know example? The case with star is with 1, star is with n. Okay? And in graph case, let's when this 1 is one eigenvalue. Okay? And if 1 is one eigenvalue, then when it like which graphs are there which have algebraic connectivity as 1. In star case, you know this as means in three case. So stars are the only things with this. But in graph case, these are questions. First question is answer. Okay. First question will be n is one eigenvalue. Then the graph is the join. So that's the if and only one. This is the question I'm asking you, so you can solve it. Okay. The second question is open. You can consider the second question, or you can think about when the graphs, which graphs have algebraic connectivity one. Okay. So these are the questions which are interesting, but not this one. Another problem that like alert and Liam and others they have considered, that is which are the graphs which have distinct integer identity. Okay. So when I am saying that distinct integer identities will be there, so how many integers can be the possible eigenvalues, Laplacian eigenvalue? Your largest eigenvalue can be n, right? And the smallest is 0. So you have how many integers? Like n plus 1 integers, which can be eigenvalue. Okay. Now you are saying that you want distinct eigenvalues. One integer can be 1%. Yeah. So one can be. Okay. So you will think that you are taking the numbers between 0 to n, and then 1 you will leave. And they will ask the question, what are the graphs with that split? Okay, so that's the question that was posed. And so I'm denoting this way. If I is taken out, then I'm denoting the set as SIN. Okay, so the question is, what are the graphs which will take the spectrum SIN? Means I is missing all other integers. Okay, which graph will take this spectrum? We'll say that this is Laplacian realization. Or this spectrum. So this way is defined. So asking whether such graphs are there or not. Can you give one small example, like thinking like, let's say taking P, what is this? P. So P, C3. C3, what are the vertices? What are the eigenvalues? C3 is K3, right? What are the eigenvalues? 0, 3, 3. 3 is 50. Now we don't want to. So P3 if I take, what are the eigenvalues? 0, 1, 3. So 2 is missing. Okay, so that is one example. It's a graph of 3 vertices, and the eigenvalues are 0, 1, 3. So 2 is missing, your array is 2 in. Okay. So can you give another example? you have to know the again values. Maybe you are not the one to the rest. So if you don't know the again values of the graph, so we can answer. So I have listed here. This graph will have to observe the things of the graph which are coming up. So if you take K2, K2 is with eigenvalue 0 and 2. So 1 is missing. Okay, so this is the smallest one. Then B3. Then all the I have written here using joint and union so that you can calculate. Okay. So K1 joint, K2 union K1. Okay. If your joint union operation you will apply, you can calculate this also. So let's say like K1 joint K2 union K1. If you draw it, how it will be? So it's a triangle with a triangle. This one. Similarly, the other graphs are like you can see one number is. But the first graph was 2 vertices and 2 is there. And the other number is 1 is this. And P3 is 3 vertices, 3 is there. The number missing is 2. And the third one is with how many vertices? 4 vertices. And 4 is there. Missing number is 2. Similarly, the fourth one there is 5 vertices. Okay? And 5 is there. 1 is missing. Similarly, the other one that is also with 5 vertices. Okay, here 3 is missing, but 5 is there. Oh, what they prove that if you take out I and I is between 1 to n minus 1, then such graphs exist. It can be had. So they provided a construction using join and union. Okay, so such graphs exist. And they put the conjecture that if you take the eigenvalues 0 to n minus 1 and leave n, such graphs do not exist. Okay. And if that conjecture holds true, then all other graphs which we are constructing, they are also unique graphs. For each one, you will get one graph. Okay. So those are done, you can go through the paper. But this is the conjecture you can do. And then for 11 vertices, there is no such graph. Okay. If you take the eigenvalues 0 to n minus 1, no such graphs exist up to 11 vertices. And some other authors, they also prove that after a large number, you don't have such graph. Like if you take a very large, they're given some. So after with like more vertices than that number, you don't have such graphs. Okay, so the conjecture seems to be true, but people have worked also, and what has been observed that if such graph exists, okay, then diameter can be restricted for such graph. So its diameter will be 3, and its complement diameter also 3. So if the graph has 0 to n minus 1 eigenvalues, is what about the complement of the graph? What will be the eigenvalues? The same less. So G and G complement both have same diameter 3, and they will be with these eigenvalues. So those are the certain developments you've done, but the conjecture is enough. Okay. So if such eigenvalues will be there, your characteristic polynomial also may vanish. Okay. So it's coming from the spirulina. So I'll ask another question you can think of. I'll take these numbers. Okay. So I'm writing first 0. Then I put 1 mark. Then I put 2. Then I put 4. And I 3 and then 4. The number starting from 0 to 4, but I have written in this one. Now take all numbers. Okay, starting from 0 to 4, so my set I have named as 4. It's containing the number 0, 1 twice, 3 twice, and 2 twice, and 4. Okay. So the question is, can there be a graph on 9 variables taking this pattern? Okay, so realizable variables. Can there be a graph with this pattern that you can think? So here I am taking S4, but the same question you can ask for any n. So then you are again below the lattice. Okay. So can there be a graph with these identities? Okay, so both the questions are related. So this question then. We can play first. Okay.